Very pleased to introduce the first talk. So tonight we have the team from GPU Audio here with us. Welcome and thank you so much for joining. There are quite a few of you, so I'm not going to introduce you all by name. Instead, I'm just going to maybe let you introduce yourself.
Yeah, so please meet me. I'm Sasha. I'm co-founder of GPU Audio, one of the architects of the original technology and platform, the entire solution, and one of the, concept creators. Today, please meet my co-founders, CTO Alexander.
Hey everyone, very nice to be here. Thank you for the opportunity. I am the Alexander Prokopchuk, the CTO of the GPU Audio. Please forgive me that my current image and sound are not ideal. I'm currently on the road, so I don't have my favorite SM7B with me, so sorry for that.
Yeah, Alexander helped us a lot to write down the DSP, redesign them, and fit to the systems like a GPU. And please meet my co-founder. He's right here with me, Basil.
I'm Basil.
Yeah, he's our chief product, and this is the first guy who came to me with the idea creating the GPU audio technology. I was thinking previously that it would be quite easy. Well, you know, a few plugins on GPUs, not a big deal. But then it turned into the entire new standard we will talk today.
Fantastic. Right. Yeah. So what are you going to be speaking about today?
So today we will show you the web demonstration about how the technology, what is the technology is about. We'll show you the hardware setup we have today, and this hardware setup and some software we developed so far. This will stream directly to the Zoom conversation, and I believe it will be streamed directly to the YouTube, so everyone can hear that it works. Everyone can see that it works at low latencies. It works remotely between the two connected together laptops, which is another scenario. And we want to prove to everyone that it's actually possible to maintain GPU processing at latencies as lower as 1 millisecond, including through the local network, whatever it is. So we want to show this use case. We also want to talk a little bit about the technology, how it was possible, how it was done by us, what are the key challenges we accomplished so far, what we are going to do with this technology, with this platform, what we want to, you know, what the message we want to deliver to the Prodia community. And if you allow me, I'll start.
All right. So yeah, I guess you're ready for you to start. I'm really excited about this because, you know, the topic of audio on the GPU is really quite new and exciting. And when we saw your proposal, we just knew we had to get you on the meetup. And so, yeah, take it away.
Before we start, really quick, for people that are in the chat that may have questions, please prefix any of your questions just with the word all in caps question, just so we can see that and we can ask the GPU audio team after their presentation.
Okay, let's crack on. So first of all, guys, let me show you what we have for today, what we will stream today. This is a MacBook I used to, this is another Zoom window. This is just a MacBook I used to speak with you. And currently with my phone, I'll show you two particular laptops. This is a Gigabyte iRAW that has the RTX 2080. We currently don't use the RTX 2080. This is the client side, as you can see.
I'm sorry, I don't think you have the camera switched to the device because I don't think we can see it.
In another window in Zoom, actually.
Oh, is that being streamed into the?
Yeah, yeah. I just put it back to gallery view so they can see it.
Okay, cool. Thank you, Josh.
Yeah.
Sorry for that.
All right. So may I ask Basil to stream, you know, the client side window, which is the Reaper.
Oh, sorry. Let me.
Can you see this?
Turn on the
just one second. Hold on. All right, guys, you have to see the Reaper window, right?
Yep.
Yeah, great. So here you can see the ASIO, what is this? Guitar Rig Mobile with 96 kilohertz, 96 samples, 1 millisecond buffer latency. This is a client side. So what we will do with this gigabyte laptop, we will offload the entire tracks. We will process here through the Thunderbolt-free connection. If you can see this, I'm sorry. This Thunderbolt-free connection to this one laptop, which is their Razer Blade with another RTX 2080 with a server running on that GPU. I'm sorry. So maybe we can start with one simple delay, and you will see this. You will see this working, and you can hear the result. You know. So, shall we start? All right. Let's open the effect. So, guys, I hear that you hear that there is a sound, right? 1 millisecond latency. So I'll ask Basil to add more processings, like one simple delay, and you can hear the result. And oh, sorry. And here is just the simplest delay. Not sure if I can show you the traffic. Could you open the task manager? The traffic goes through the Thunderbolt 3. As you can see on my phone, sorry, the GPU 0 is Intel UHD, and the discrete one, RTX 2080, is not used, but the traffic goes through the Thunderbolt 3 connection with one simple delay, 8 megabit per second utilized. And here as well on the GPU server, the traffic started, and the RTX 2080 actually started work. If I'll ask Basil to duplicate this track, just simply duplicate this, you can see again on my task manager, please show it, that traffic went, you know, doubled with double size, as well as here on the server side. And also the GPU one also doubled, but this is not actually the payload. It's just, you know, the driver calls, and that's why Windows show this in, you know, double time. So what I will show you right now that we actually managed to work it within within 1 millisecond latency. Maybe Basil, you have to, you know, turn knobs, and let's speak about the simplest delay. Let me switch everything on. Yeah. So what you see right now and hear right now is just the simple delay with infinite impulse response filter, with the tape effect, and feedback loop, and these sort of things. I'm sure that you can hear them pretty well on the YouTube. Do you guys? I'm looking on the YouTube chat. Do you guys hear it? Do you guys hear any difference? Oh, okay, I hear it. Okay. So, okay. What I will ask Basil to do, just to duplicate, you know, like more delays. And then I'll ask Basil to follow a contract and let me hear some changes. So you can see that we also utilize the initialization step. It requires some time, you know, to run the GUI and etc. But anyways, I'll ask like add up to contract, let's say, or yeah, and lower. Okay, we have like technical issues. We have to restart just for a while. Sorry. What I want to say is that this works through the network connection, and we use the RTX 2080 on the razor blade, and this is delivered across the 1 millisecond latency, the round trip, right? So what we have on the client side, this is the ICO for all drivers utilized, and we can run any sort of the processing remotely or locally. It doesn't matter at all. So I'll ask Basil to restart it and just to make more tracks, and you can see that actually traffic goes. And then I will ask him to add like different effects developed so far. So for today we developed delay, flanger, chorus, phaser, multiband distortion, parametric equalizer, exciter, reverb. We're rolling out the reverb, the hybrid one, and we also implemented some compressors with emulations. We have some technical issues because it's an alpha version, but there are some bugs anyways. So let's start over. Let's start over to add more things. Could you show like something else, like not delay? I don't know, like anything else.
Sorry, Sasha. I see in the chat that the viewers are saying that we should do the DAW signal louder.
So Basil, please just add, very few effects, and then just. Okay, he needs to turn on the demonstration again. Yeah, so we have many more of them. I'm not sure whether we can show all of them right here, right now. This is like the alpha version. The alpha version we are continuously rebuilding and testing. So that's the reason we don't have it in public yet. But I believe that will be containers.
Одной веры на двоих, жизнь, лифт вверх-вниз, черновик картины, снова чистый лист, она как будет сидеть блок до утра, в поисках правды, под стук дождя, крутить слова в голове, чтобы понять, что произошло тогда, он же сказал вернусь, дождись меня, а дальше стрелки, часы, он навстречу, как-то хмуро, конец разговора, пуля, дура, и, наверное, он знал, что все не так просто, и это кино для взрослых, где он уже не вернется, но он улыбался тогда, да. Спокойно, жаль, что жизнь одна, но она того стоила.
Right, anyways, because we're having a text with more devices, more planters whatsoever, it will work. With 1 millisecond latency, and maybe we can add more, different effects with different types of effects, and use the solo modes, like here, like phaser, I don't know, like anything like that. Yeah. So that stuff. Are you guys? Yeah, I hear it. Great.
We can't hear what you're saying over the music because the music's too loud. It's actually in our ears now. But
yeah, sorry, it's real time.
Yeah, I think there are a lot of people are really impressed with what you're doing here. I think there are a lot of questions in terms of the how you're doing it. So it's great to hear what's happening under the hood, what sort of API you're using, and just digging a little bit more into the technical details.
Okay, can I just do the last thing, in this demonstration so everyone will believe it? Because for me, it's very important because people started arguing in the web forums that it's impossible to do. The GPUs are very, high latencies and that stuff. So I want you to show, sorry, 1 second. Okay, guys. So I wanted to show you, this is traffic here on, this is traffic here on the GPU server and GPU 1 in Ethernet, Thunderbolt. Oh, sorry, it's switchable. What I will do here, all right. It's crashed, but anyways, okay, you can see that it worked actually. Anyways, and GPU 1 and Ethernet, we have bugs, I'm sorry, but anyways, this is something I wanted to show you that actually if we will break the connection, there will be no Ethernet, no GPU 1, but it's crashed and so on. And so these things are working here. Okay, if I can continue right here on my MacBook. Well, there are lots of things you have to do if you want to consider to utilize your GPU to process audio. Well, whatsoever you have, like desktop, laptop, GPU server, blades, it doesn't matter. If you want to process audio through any sort of APIs like VST or audio unit, you first have to understand how you can achieve the low latency work on the GPU, because this is something that you cannot do with any SDK available to this date, like, I don't know, like CUDA, like DirectX, any sort of shaders, anything. We used anything, like almost all of them to organize this stuff. So it's impossible. There are simply no such calls to organize many tracks, stereo tracks with the many channels, and there is no way you can organize all of these tracks and upload it to the GPU using some asynchronous API. There's no way to organize it. So you have to implement this. The second big problem why you cannot utilize GPUs as simple as it is to accelerate your algorithms whatsoever they are, with the recursive algorithms or well-parallelized algorithm, doesn't matter. The second thing you have to consider is that the GPU is, which is well known, is a SIM device, which means that it's single instruction, multiple data. So you can run like a very few tasks for many data. And the audio, it's one-dimensional arrays usually, right? For 96 kilohertz, 96 samples we showed you previously. For 1 millisecond, it's just 96 samples. So you have to dispatch many tracks in parallel with the tiny amounts of data if you want to organize the recording sessions, live performances, and that sort of stuff. So GPUs, from the very basic, are not designed to do the audio processing work. So how did we get this? So first of all, we implemented the component, the basic technology we call scheduler. The scheduler usually packs all of the data to the GPU. It unites all of the data in a few streams, or as many as we have the real stream, the PCI Express streams. We pack them all and we deliver from the client to the GPU server. So there are two basic things here actually. The client side, which is just the VST-based plugin we developed so far, and the server side, which runs all of the payloads on the GPU. So again, the VST plugin and the GPU server. So what we did, we implemented the copy manager for the scheduler that allows us to unite all the data and to transfer them to the GPU server and device and return it back within latency scopes as low as 1 millisecond latency. So this is something you cannot do with CUDA or I don't know, like OpenCL, OpenGL, DirectX, Vulkan, whatsoever, Metal, I don't know. This is something you cannot do, but you can do this using the driver API and the low-level API, which is for the NVIDIA cards, PTX ISA. This is like a cross-platform assembler NVIDIA developed for all of the NVIDIA GPUs so far. So this is how we managed to run many streams. And you can find some videos on YouTube that are related to these cases, remote computing cases that we run 45, 90 channels and even more within 1 millisecond latency. Actually, in tests, we do run hundreds or even thousands of streams without the VST API, because the VST, it limits our bandwidth because we cannot manage threads of the DAW. So this is a minor issue, but whatsoever. The second thing you have to consider in order to implement GPU acceleration of the algorithms is how to make GPU running many different tasks. Because, for example, for the infinite impulse response filter, there are feedback, right? This is just the nature of infinite impulse response filter. In classic design, you cannot parallelize infinite impulse response filter, but there are some parallel designs of it. And for example, for reverbs or for the convolutions utilized in the convolution reverbs, there are thousands and thousands or even hundreds of thousands of multiplications. So you have to figure out how you can run 1-2 threads algorithms on the GPU, as well as how to run, I don't know, like hundreds of threads in order to deliver results in time. So for this purpose, we implemented in the scheduler algorithms that turns GPU from SIMD device act as a pseudo-MIM device. So you can dispatch many requests coming to the GPU in real time in low latencies with whatsoever processors are, like I don't know, like delay with the infinite impulse response filter, like 2 threads utilized, 4 threads utilized, whatsoever. For the reverbs, 256 threads utilized, it doesn't matter. So you have to understand how you can run it. We also achieved this with utilizing PTX ISA. So the core technology was implemented on the top of the cross-platform PTX ISA, and soon we will develop the same stuff for the AMD Radeon GPUs. So this is how to actually organize the payload from the GPU server to the exact device. But the platform itself, the technology we used, it's very complex. It has many more components I want to talk a little bit today. So as you saw today, there is a Reaper DAW, and we run the VST plugin, and we have like a fixed chain on the very bottom, 10 cells length chain, and you can instantiate any sort of effects you developed so far, whatsoever it is, delay, I don't know, like multiband distortion or phaser and that sort of stuff within this fixed chain. So basically, on the VST part, we implemented our own VST plugin that represents the 10th length fixed chain. And for this purpose, we used many advanced features, advanced technologies that are not in the common use in the JUICE community or the VST community so far. For example, we utilized Ceph, Chromium Embedded Framework, and JavaScript to render any GUI we have so far. I will show you on the very end of my speech how we did that. This allowed us to recreate any sort of GUI with photorealistic quality, 4K, high definition stuff whatsoever, just as making the website, And we embedded the Ceph as a Chrome-based browser directly into the editor of the VST part. I saw that there were quite some attempts to bring in the Chrome to the Juicy and to the VST. So far as I know, is that the only companies utilized the Ceph in the production area is just BioSFX, which is the Positive Greek company. Or I can mix some names whatsoever. They only managed to do so. We used this Ceph in order to reorganize the GUI rendering part, because this is the first engineering task you have to solve. So for example, for the Gigabyte or for the Razer Blade we have today, we have basically two GPUs. One is Intel UHD, which is typically embedded into the Intel-based desktop laptop processors, right? And well, the AMD APU, they have also sort of the embedded GPU solution, and the discrete one. For the discrete one, for the laptops, it's usually the NVIDIA GPU cards. If you have a modern laptop, like 3 years old, maximum 5 years old, it's 100% that you have the NVIDIA. For Mac OS X, for sure, right now it's complicated because, well, they switched from the NVIDIA GPU 5 years ago to the AMD Radeon, and right now they rolled out their own silicon, so it's quite complex for them. And we used Ceph in order to tell that to editor, okay, you don't need to render these knobs and buttons by NVIDIA discrete GPU. You have to do it with Intel UHD. So that's how we solve this problem, offloading all of the stuff on the discrete powerful GPU. So we utilize Ceph to render the GUI. Another thing, we have this like advanced technology, I called it. So the protobuf.js. This is actually the binary serialization stuff. And the binaries, Basil wanted to show you that it works actually in web. Yeah, you can show this F12, you can show them, they will see that anyway. So as you can see, guys, this is a web-based. You can run it right here locally or remotely, and I will return back to this topic because we developed more than that. So as you can see, everything is web-based, JS-based. You can do any GUI like by click of the fingers, which makes lots of sense. So more cool stuff we used is protobuf.js. Why the binary serialization is very important for the product developers community. Because guys, if you have like really hard and complex things to deliver to the end customers, like, I don't know, like modular synthesizers, tens and tens or even hundreds of variables you're utilizing in your code. So without if-else's switch cases, you can use the binary serialization, and Cap'n Proto and protobuf.js is definitely the shortest way to organize any sort of data flow between any component you're utilizing. Like on the JS side, we have protobuf.js library we complemented with the community. So we linked all of the knobs, all of the data using the simplest protobuf without any if-else's switch cases. And every time we want to deliver the knob changes to the processor, minimizing the traffic, right? We use the protobuf library, and we also support the protobuf library across the editor, VST editor, VST processor component, as well as GPU server component, and some sort of the integration for the device side. So again, we utilize protobuf in order to deliver the change sets on every, I don't know, like millisecond, microsecond, whatsoever they are, right into the time across all of the call stack directly to the device. And we also utilize protobuf in order to return back the data, audio data, spectrum, and that sort of things. So protobuf is another key component of the whole platform and the entire core technology. We also utilize the IPC components, inter-process communication. I know that lots of things I am describing right now, maybe it's very, very complex for you, but I want just to show you why we use it. So we use the inter-process communication like Windows-based, because we have this implemented currently for Windows and NVIDIA first, and we can do data exchange in between the plugin, VST plugin, and the device within latencies as low as even lower than 1 millisecond with IPC. So you can run this across any hardware setup use case you have it. So imagine you have like a studio with GPU server, right? Like let it be Windows running 3 GPUs, and you have like tiny rooms with the client side with I don't know, like laptops without discrete NVIDIA GPU whatsoever. You can connect using the Ethernet cable, Thunderbolt, Wi-Fi 6E, whatsoever. You need just 1 gigabit per second. And utilizing these IPC components, you can deliver the data within 1 millisecond latency. How about that? So that's actually what we streamed today. We didn't want to show you the local setup, well, because it's okay. We managed to run latencies locally, right, on the single device like laptop or desktop. We wanted to show you that we also implemented the IPC components, so we can deliver the data through the network in latencies as lower as 1 millisecond. So this solution, if you want to develop the GPU audio SDK based solution, you can run it both for recording, both for live performances and concerts, and post production whatsoever, because it supports the solution supports the IPC components. So the typical stack again is VST plugin part, which is the editor based is Ceph running the JS application. Then it goes through the controller integration to the processor part of VST. It unites all of the data for the all effects if you turn the knobs or if you perform in the automation lines for that. Then using the IPC across all of the way, you're packing the data using the protobuf, sending it to another component GPU server, which could be run on local PC, laptop, desktop, whatsoever, or remote one. Then you're dispatching this stuff using the scheduler, making cool stuff computed, and return it back. So this is like very brief understanding of what we're doing. Maybe you want to ask questions here, any of you?
Yeah, so there are quite a lot of questions.
There
are quite a lot of questions on the chat. I can maybe just ask some of them, because I think even if some of them you answered in the chat, I think it's still beneficial for people who are watching the video afterwards. So there were quite a lot of questions on like what API you're using. I think you kind of answered that now. So, like there was there's one question by Pavel Kopot saying, does this mean that you actually wrote a custom driver for this specific RTX 2080 on a GPU server? Is the GPU server still capable of using this GPU for driving its display?
Yeah, this is a good question. The answer is no. We're utilizing the driver API, and we're utilizing sort of, let me call it injection, our own custom made code on the top of the driver API and PTX ISA in order to inject the scheduler, like sort of middleware, firmware for the GPU, but we do not utilize any interruptions and that stuff. We're actually not fully controlling the GPU, but we do that with some tricks applied to that. So if you do some system setup, as we did for this web demo for today, you would be able to isolate your discrete GPU and make it computing, only the audio processing thing. So no, we are not implementing any driver, but we do some top on the top of that. So that's how we are bringing the entire technology, and that's how we lowered latencies as low as 1 millisecond or even lower. And that's how we are able to run everything as you saw today.
But it sounds like you still need 2 GPUs, right? You need one for like the usual screen and everything, and another GPU for all the stuff that you're talking about, right?
Yeah, but the good point is that well, this is, first of all, if you want to be sure that you can do the work with the latencies as low as 1 millisecond, yes, you have to get 2 GPUs. But the good point is that 95% of laptops, accordingly to the Steam statistics, they have the discrete GPU and the embedded GPU. Desktops, I don't see any problems to purchase 1030 passively cooled for $30, and it will do all of the stuff. For the GPU servers also, you can do anything you want. So this is not a big deal. And also maybe you guys on YouTube stream, and Josh and Timur and Paul maybe also have an interest. We started implementing this thing with the Windows and NVIDIA. This is not the limitation. This is just the point where we started. So yes, we have plans to deliver first the AMD Radeon GPUs until the end of this year to the Windows. Then we will understand what are the plans of the Apple on their silicon and their GPUs, etc. Maybe they will keep the AMD Radeon in the professional editions, of MacBook Pros, 16 inches and iMacs and that stuff. If they can keep it, we'll also deliver the audio unit integration for other DOS for the Mac OS X system as well. So yeah, and actually this is the reason why we implemented IPC components, because we also wanted to deliver these sort of solutions for any sort of setup that user have.
Okay, well, yeah.
Can I continue?
Yeah, sure. I thought you made a pause, so I can ask another question. But just keep going, and I'll ask more questions when you're done.
Yeah. Well, the reason why there were some attempts here actually in utilizing the GPUs for pro audio acceleration, like Liquid Sonics. Let me name of them: Liquid Sonics, Acoustic Audio, Neil Schneider. They released some products, but the problem was first latencies, and they cannot manage to run in latencies as low as 1 millisecond. They only managed to run it with a 2,000 samples more, or even more than that. And they cannot manage to run many instances with different types of software simultaneously, which makes a lot of sense. So we have to bring sort of SDK and API. And right now I'm continuing my speech to what we want to bring to the community and why actually. So we developed this proprietary technology scheduler. It will be not open, unfortunately. First of all, because it's quite complex. I believe that not every NVIDIA guy understands what we did so far. Me as HPC scientist and other guys, we have like six PhD or even 7 PhD people working in the GPU audio. And it's quite unique technology how we managed to run lots of streams, like virtual streams, tracks, and channels, and dispatch them within 1 millisecond latency. So there's no point to open the technology for the rest of the users because they don't know how to improve it, right? So, but the good point is that we want to make it for free for everyone to contribute to the GPU audio-based products in the future. So we are announcing that we want to publish the SDK soon. I'm not gonna disclose the exact terms because this is again the subject of our understanding, because the technology is quite complex, believe me, and we do not want to share all of the pains and the problems we managed so far. We want to share, some complete solution so you can use it with some guidelines, and it will be enough to make some good products. So in this SDK, in the future that we will publish, you will be able to write any sort of Chrome-powered solution, GUI solution. It can be whatsoever you can run. I don't know, like JS-based or PHP-based, whatsoever GUI. It will be very easy with our own custom-made stylized knobs. You can stylize any GUI like within click of the fingers. By click of the fingers, it will be very easy for you. Using the protobufs, you can Google it. It's very easy to organize, controller part, bringing the controls to the processors. Just writing down the proto file. It's very easy. And you will receive all of your GUI, all of your controls on your device code very easily with our protocol generation feature in the SDK. What you will need to use in the SDK is our own implemented simplest libraries like, I don't know, like FFT, any DSP parts. I will ask Alexander to continue just within 1 minute. And you don't need to manage threads. And this is the main feature we want to implement for SDK, because the reason why people are not utilize the GPU so far, because different DSP algorithms has different problems. Let me name a few. For example, infinite impulse response filter. You cannot parallelize the classic design, but there are other designs. For example, you can make the decomposition of filter orders, and you can run them in parallel. So that's how you achieve the the parallelization process for this purpose. There are also some other designs like Mr. Zavalishyn zero delay filter design and that sort of stuff that you can use as workarounds for recursive sort of algorithms. Or let me name like compressor. In the compressor, there is the detector part, and detection actually needs to check every single sample that did you break the level, did you trigger the level in order to apply the attack or release mode or not. So in this case, you can hack it. You don't need to check it every single sample because you cannot hear this. You can do that, for example, each 32 samples, like 32 threads parallelized. So people are simply not able to hear any difference between the triggering, each one sample or each 32 samples. For sure, there are some problems with automation here, but you can use these hacks in order to deliver very parallelized code. So again, in the SDK, for the device side, we don't want you to manage threads. We don't want you to think about how to port the exact algorithm to the device. You just need to run our own library calls, like I don't know, like use the FFT, then multiply stuff, and then do something else, and this will be as easy as you can do for CPU work. So I want to ask Alexander, our CTO and DSP engineer, to tell to the community what we implemented so far, what components we implemented for the GPU, and what will be available on SDK once it will be published.
Okay, yeah. Thank you, Alexander. So regarding the DSP components that are already developed as part of the GPU audio SDK, basically the idea of the SDK is that we do not want to limit our users to the components that we developed ourselves, but to use them as an examples or use them as basic building blocks. So as Alexander mentioned, and as you've seen on the live demonstration, we have developed quite a few of classic, so to say, processors like delay, phaser, flanger, reverb, equalizer, and so on. So the building blocks of those products, they are pretty obvious. So it's IIR filters, it's sphere filters, it's frequency and time domain convolution, it's fractional delay lines, it's FFT, IFFT, it's synthetic reverb schemes, comp filters, all pass filters with delays, all kinds of crossovers, band limited oscillators, distortion emulation, envelope builders, the parts that consist of digital compressor and so on and so on. Some of those algorithms, they're translating to the GPU just fine algorithmically. The good example would be the convolution. It just scales very well in both frequency and time domain cases. Is just great. With IRR filters, it's the complete different story, so to say, because each single output of the second order IR filter depends on the previous two outputs. So it's a recursion, and it cannot be parallelized directly, but we managed to develop some kind of novel approaches of cracking those things and evaluating IR filters on a SIM device fast enough and efficient enough, so to say.
Yeah, if I can continue, Alexander, I can tell you more, guys, is that we're not just, with the scheduler, we're not just managing to run a single instance again, a single instance of the processor, let me say it. So, because processor, it consists lots of different things like, I don't know, like components, DSP components, and we actually internally by scheduler, we are managing running each of the components as part of the processor, and we managing to run many instances of these sort of processors. So it's quite unique, quite complex thing, and that's the reason I saw some questions here on the YouTube already. That's the reason we cannot just utilize already developed some libraries that developed already. I don't know, like QBLAS, QCino, OpenCL based libraries, whatsoever. The reason we cannot utilize it because we have to tell to the GPU and the scheduler that, okay, you're running this with this many threads and blocks, and you're running this with this many threads and blocks. So we have to re-implement all of them. But the good point is that we're gonna make it. So there are pretty standard things like linear algebra methods, I don't know, like DSP methods. FFT is FFT. So far as it supports the IE 764 standard, and it doesn't produce any sort of errors, additional errors. It can be utilized for your product if you want to utilize the GPU audio based SDK. What else I can say that as a standard, we wanted to deliver more than just the code and just the products whatsoever, our own made products or products developed in collaboration with other brands. We already contacted with some of them, major one, or with minor brands or one guy army brands whatsoever, or just indie brands, just developers whatsoever. We want to bring the entire new experience for the end customers. Because imagine what we have for today. We have three types of solutions today, hardware-based, I mean. Basically, we have the Pro Tools, its own implementation, hardware implementation, Universal Audio hardware implementation, and again, well, some other stuff, CPU-based stuff, even the Wave Sound Grid stuff. So what happens there? Well, Pro Tools, they're developing once per decade the entire hardware set, right? And they need they cost like $1,000 or even cheaper whatsoever. There are not, they doesn't have like how many, like thousands of cores. They have like 8 cores, so I'm not sure, running at 18 cores running at 300 megahertz, 400 megahertz. NVIDIA GPUs, they have like thousands of cores running in 1 or even 1.5 gigahertz. And prior to the COVID times, it cost like 400, 500 bucks, right? But again, even with COVID times and mining stuff, you can purchase a laptop with RTX 3060 for 900 bucks on Amazon. Just check it right now. It's available there, or I don't know, like $1,000 whatsoever, and it will beat it. So again, this is another thing we want to bring to the industry. We want allow the user to do not just scale the power, because if you're a Pro Tools user, you can only scale it. You cannot upgrade this because you can do that once per decade. Sorry, you can just add more hardware, and here you can sell your old, I don't know, GTX 1060, purchase the new RTX 3070. You can upgrade it. Scalable, it's scalable. So, well, I know that some solutions that work with Ethernet connections, like SoundGrid, that is tuned for the performing live concerts. Imagine that you don't need it anymore. You don't need these racks with these thousands of dollars spending on that. You can grab your laptop with thousands of CUDA cores or whatsoever, the AMD Radeon cores. You can utilize it to run, I don't know, like orchestras, record 2 orchestras, because you have all of the power with yourself, but you can grab it. It's mobile right now. If you have a desktop, okay, no problem. You can use as many cores as you want. This is the totally new experience we want to grant to the end users that will work on the top of the GPU audio ecosystem we plan to build in collaboration with the Pro Audio developers community. What's more, the thing is that things are going fast, and there is a Wi-Fi 6E standard, and it managed to run 1 gigabit per second bandwidth. So here we can actually do not utilize the Thunderbolt 3 connection we showed you today, or Ethernet. We can run these IPC components and these remote computing cases just within the air. We need only the 1 gigabit per second connection. So it also makes a lot of user experience cases that you can run for your end customers. This is very important because, well, other companies, like big companies, like big guys, I don't know, like Avid, Waves, and these guys, they're providing you the entire solution with high cost and that stuff. Imagine you don't need it. You can purchase a laptop with the new RTX 3060, $1,000. It will do anything for you. What's more, we call this feature, it's not rolled out into the release in production area. Well, we're a tiny startup, right? But we tested already this. We call it instant rendering feature, fast rendering feature. Imagine you have heavy projects, like tens or even hundreds of tracks running on the timeline, half an hour, 45 minutes, or 1 hour. With GPU, utilizing all of the cores, you can do the rendering faster than the CPU. And for this price of money, this price, you can do that as easy, because you can manage to run in parallel whatsoever effects you have. So again, this is something that CPU cannot deliver, CPU-based solution cannot deliver for you with a low price cost. Okay, you can purchase the Threadrippers, I don't know, like per $1,000, but there are 32 cores, or how many cores, even running at 5 gigahertz, right? So again, this is a question about the solution cost. With the GPUs, with the time we want to deliver to end customers, to all consumers, availability to render, like ray tracing for video, but for audio, performing the rendering and bouncing and exporting projects faster in times and tens of times faster than CPU based. And there is one unique case I can imagine, that if you run reverb with the quite long tail, you cannot run it on a single core as efficient as on GPU. So that's why it will be rendered in times slower than on GPU. And a scheduler, the scheduler component, it not just utilizes the parallelization within the algorithm instance, but also for each track. So again, all the threads and blocks, there are parallel for each track and channel within the track. So it makes a lot of sense that you, with GPU audio-based solution, you can render projects faster. And for some heavy use cases, when you're working for some studio post-production, I don't know, like making movies for big companies, where when you know, the salary for each specialist, it costs a lot. You don't need to spend like half an hour of waiting or 15 minutes of waiting each time you're pressing the bounce button. And this is something that will be delivered just within the box with this SDK. If you will utilize our own methods and you will build the product on the top of the GPU audio. So again, as I said before, we plan to deliver the completely new user experience. And maybe you have some specific questions. Oh, maybe Josh or
yeah, there are quite a lot of questions.
Okay, let's start. Let's crack it.
So quite a few of them were from like earlier in the presentation, but I'll just go through them. Wesley Griffin is asking, what sort of utilization of the GPU are you getting? Is the processing parallel enough to hide the GPU thread latency?
Sorry, I didn't get it. Could you start?
Is the processing parallel enough to hide the GPU thread latency?
Yeah, we managed to run within 1 millisecond latency, even with crashes. I'm sorry, we have YouTube videos without crashes. And yes, it makes a lot of sense. Yes, there is a PCI Express problem between the CPU-based solution and GPU-based solution. You have to organize the transfer over the PCI Express 3.0. The problem why other Pro audio brands still continue thinking about that, it's quite high latency. No, it's not. Starting with PCI Express 3.0, you can wrap up to 64 megabytes within 1 millisecond latency. You can dispatch it, and you can do all of that stuff within this 1 millisecond latency scope and 64 megabits per second bandwidth. If you can wrap it everything, you can support this scenario. For PCI Express 4.0, it's like how many? Like it's 4 times more. For PCI Express 5.0, again, you see?
Yeah.
So, yeah.
So I think the question of latency is kind of the crux here. This is what kind of everyone's interested in. So just so Pavel Kopot posted quite a few questions on the chat here. He's saying, why do you think all existing GPU APIs like OpenCL and others that you've mentioned introduce latency and PTX assembly does not? It's so strange why there is no general purpose low latency GPU API. So basically, if you found a way to do this, why isn't there already an API for this? This seems to be really weird. So he actually goes on to say, if low latency on GPU is possible at all, you know, it's just strange that there is no straightforward way of doing this. So there are no APIs for it. But you know, what basically another way of thinking about this is what bottleneck is causing it, because PCIe by itself must be pretty fast, right? So there is also GPU firmware running some code, OS driver, there are GPU APIs. So where's the bottleneck there, and why do you not suffer from that?
Yeah, so this is a great question. I can be almost 100% honest here. Well, because we're a startup, we're backed by VCs, and this is innovation. And you know, I spend a lot of money of investors making this sort of stuff. But actually, this is one of the few questions that, you know, opened the doors for the GPU audio implementation. What I can tell you is that, well, there are some methods you can utilize in OCL or CUDA, like work groups. They were recently introduced in CUDA 9 or something. And also there are overlapping feature and a synchronous feature you can utilize to organize something. At least you can deliver one ping pong stuff very quite fast, but not every single time. And I cannot answer this question, how you have to organize it continuously, because it's actually the technology implementation, sorry. The second thing is that the working groups is the way to organize payloads on the device side with different blocks threads configuration. So you can do that with work groups on the CUDA or OpenCL, but you have to add something more than that if you plan to run like literally anything on the GPU, like any sort of the plugins, third-party developed plugins at any time you want to run it. So again, all of the answering all of the question, you have to implement what we call scheduler again. So the scheduler is one of the answers why it simply was not possible to do with generic APIs, and why these methods are not well presented in the API still. Maybe with the time, NVIDIA will produce some sort of the approach of scheduling these things, and they will develop some additional APIs to organize everything. But you can do, I can be like 100% honest here, you can do or low latency stuff, but not so much like 4 streams or 10 streams on the CUDA with a generic API. Or you can do some one-typed many instances payload running on the device, but you cannot do this simultaneously without going to the PTX ISA level. So again, the scheduler have to be implemented somehow by NVIDIA, by GPU audio team, whatsoever. You have to provide the full control of over the resources, starting with streaming and finalizing how do you want to treat your processors with how many blocks and threads. So yeah.
I'm sorry, may I add my 2 cents here? So basically, to summarize what Sasha said, the, so to say, metaphysic, the part of the question, why the currently generic purpose APIs doesn't have those kind of abilities. Basically, it's history. As we know in computer science, it's always latency versus throughput optimizations, and the GPUs historically was used as high throughput devices. So all the APIs are constructed in this way, but this doesn't mean that those devices can be used another way, and that's why where we come in. Thank you.
Thank you so much for the thorough explanation. I just have a couple more quick questions about this, and then we move on to other questions. So how much of the GPU are you actually using? Like how much of the like utilization?
You mean what? How many GPUs we support?
No. I think how many? I'm not actually an expert. It's a question from the chat. I guess how many of the available threads or something like that? Like,
yeah, all of them. For example, for the latest GPUs with tensor cores and that machine learning stuff, they have more than just CUDA cores, like more than 6,000 or 8,000 of cores. You can actually add some machine learning tensor cores to do some machine learning stuff, cool stuff, convolution, neural networks and that sort of things. So yes, we can utilize all of them. We don't need, yeah, we can control 100% of the GPU. That's the reason. And that's why the reason I mentioned this cool feature, we call it faster rendering, instant rendering, because we can utilize all of the cores if we have well-parallelized algorithms to render heavy projects really faster.
Okay, thank you. You mentioned,
sorry. I'm sorry. Just another 2 cents from me. Just for example, of how much in the current web demo that was presented today, each track from the door utilized 96 threads from the GPU.
Okay, I think that was exactly what was asked. So thank you so much. There was another thing. So you mentioned 1 millisecond at some point when we were talking about latency. The question is that round trip or is that dispatch?
No, round trip. We do within the buffer. We understand how it's important. We don't add any additional buffer. So yes, we are utilizing to offload from the memory of the client, from the VST plugin to the IPC connection to the TCP/IP stack using the Thunderbolt 3 USB-C connection to another GPU, dispatch it on the GPU server to the device, compute on the device, and return it back using the network and all of the components. Yes.
That is super impressive. That is super impressive. It's quite mind-blowing. Thank you. I guess there is another question, kind of more general, like, what are the advantages of using the GPU for audio kind of in general? Are there really enough things that require this kind of parallel processing to like get a significant performance boost from what you're actually doing? Like, you know, as someone who's like practically, you know, making music or something like that?
Yeah, this is like the most popular question from the pessimistic part of the community, because, okay, like some of the users, they don't face two basic problems like dropouts, because of they cannot run many instances in low latency, so they have to increase latencies to avoid the dropouts, right? And if it doesn't have these problems, the question here arises like, I don't need it because I don't have this sort of problems. I don't need to offload from CPU and utilize my GPU, right? Yes. But you know, if you run, I don't know, like Abbey Road chamber or something like that, 70% CPU usage per single instance, right? If you run complex products like synthesizers, I don't know, like Omnisphere, you have to add more latency just right off the box in order to deliver the result. Like for the Omnisphere, how many? Like 2 milliseconds, right? So yeah, 2 milliseconds you have to add in order to process it. So if you want to run within 1 millisecond latency, it's 3 just virtually in the program stack, and then it's added like hardware I/O and that stuff. So we're not just accelerating, we're not just offloading, we're also providing more features like instant bounce feature that we will introduce in the future. We also introduce unique use cases. You can upgrade it. You can upgrade CPUs for sure within the socket, right? And the PCI Express, it's not you know, the thing that is upgraded each year like a socket, and you can simply sell and buy the new one. And also we provide the solution for the remote computing feature. So again, here I see lots of them applications in many different fields, like recording in order to lower latencies and to you know, to have to do not pay latencies by CPU but by GPU. It does nothing currently while recording, so why not applying the effects while do the low latency recording stuff, because it's, well, convenient way to do the recording in the studios. For the live concerts, again, the latency, you can bring all of the stuff, like all the racks, I don't know, like any sort of hardware solution, or you can bring the only laptop and it will handle all of that. For the post-production, if you're rendering, bouncing, exporting heaviest projects, you can do that easily with many cores of many GPUs you can utilize, right? And again, this is not so price hungry. So regardless the mining time, you know, because, well, currently with laptops, again, it costs like $1,000. You can purchase the RTX 3060. So many fields of application, and I think that there will be lots of pessimistic people that don't want to utilize it. Again, I do understand that people who spend tens of thousands of dollars on, I don't know, like Avid Pro Tools and hardware stuff, they will not switch to the GPU audio, definitely, because they invested into it. So that's the reason we came to the how to say, the most enthusiastic and innovative community that see the future. And we believe that the power of the GPU is the future for the Pro Audio, as well as the future of the new, more complex devices and processors and plugins. Because as you guys know, RTX voice.
So here, I think it's a question. It's another question which kind of goes with that really nicely, which is there are actually other attempts to have programming languages that kind of exploit forms of like hardware acceleration or like domain-specific hardware things for audio, like in particular Forst and Soul, which are domain-specific languages that target, among other things, also potentially GPU audio. Have you looked into this? Have you compared what you're doing to Faust or Soul? Have you talked to them? Are you aware of these other technologies?
Yeah,
Sasha, would you allow me to handle this one?
Yeah. Please
Okay.
do.
We didn't contact the Faust or the Soul team yet, but we are well aware of them. I'm personally monitoring them. Another thing that I don't know, it was mentioned in the chat or not, just recently the HPVM 1.0 was released, and it's another thing from the same field. It's basically an LLVM-based compiler for CPUs, GPUs, FPGAs, and everything. Currently, we do not support. Our SDK doesn't support Faust or Soul or anything like that. Why so? Because as Sasha mentioned, the first and the main challenge that we faced is that we need a technology, this PTXSA code, which allows us to execute those things in the matter that is needed in the audio DSP. And then they know the sort of assembly that runs this good. Then we can think about compilers or translators that produce such code. So it's kind of one of the next steps. What probably will come, yes, because it's very promising. It's very promising.
Yeah, I agree. That's very interesting. So Josh, how are we doing with time? We have like a few more questions. I'm not sure if we should wrap up or we have time for them.
Maybe we can go for a couple more. Seems like quite a few people are pretty stimulated by this conversation. So I think let's keep.
So I have like 4 open questions still, and I think they're all pretty interesting. So I think it's worth spending just a few more minutes on this. So one question is by Hyper Eon, who's asking, how do you compile the audio code to run on the GPU? And he says, like, sorry if I missed that explanation earlier. Like, as a developer, would you as a user of your tech stack, would you be supplied a compiler, or how does that work?
Okay, so basically, if you want to use our GPU audio SDK, will be published in the future, you need to have the CUDA only. Now, for the NVIDIA and for the AMD Radeon, I'm not sure what it is. Well, it will be like the Hippify solution. I cannot disclose it yet because it's also a part of the innovation. So you have to compile it using the NVCC and CUDA code. There will be standard CUDA primitives you can utilize and write down just a simple CUDA code. If you want to utilize our own implementation of all of the DSP libraries, FFT, whatsoever, you can use it. You can include in your C++ code and just utilize the calls. It will be pretty straightforward. But in case if you feel yourself strong and you think that you can manage all of the threads and blocks and parallelization stuff, you would be also able to do that right within your code. And then you will produce like Q binaries or PTXs you can utilize and run just like that. Just put it into the program files and it will work.
Okay, so Edward Boraski is pointing out in the chat that there is actually a good GPU DSP library from NVIDIA. It's called QSignal. Is that related in any way to what you're saying? Or?
Yeah. But the point is that you cannot utilize them directly, because if you want our technology scheduler, to manage different instances of different developers, third-party developed plugins, you have to, we have to re-implement the QSignal, QBLAS, whatsoever, for our GPU audio SDK, which we will do with the community in order to, to allow all of the features work. Because if you will not migrate that, for example, instant rendering or some things will simply not work, it will crash and that stuff. So you have to migrate it. And we will also write down the, how to say, technical framework, how to migrate the components for the GPU SDK, so everyone can contribute into it.
Well, that's great, because there was another question.
I'm sorry. May another 2 cents from me. So basically, to get the picture of this, there is a Q signal. Can it be used with our SDK? Well, yes and no. We can somehow. It's similar if some code or some plugin were developed on a raw VST standard, and we want to port it to JUICE, for example. It can be done. They are both in C++, but the APIs are different. So when the processors are being written for our SDK, the code is it looks like just like any CUDA code, but it calls and utilizes additional APIs that are our scheduler APIs, which brings all the good features what we have. Because if we can surely just use the Q-signal library directly on the GPU, and there are actually some quite a good algorithms, the aforementioned IIR filter, for example, but still there will be a problem how to run 100 of them simultaneously, or 10 IIRs and 10 FIR filters and so on. Thank you.
Okay, thank you. There's one more technical question from Pavel Kopot, who's asking, have you done some benchmarks that we could look at? For example, how many like microseconds, if you have a 70 thread delay, for example, something that we showed you, and then you're processing that with like 256 sample buffer size, like a buffer size of 256 stereo samples. Like, how does that then scale? How does that change if you add like 100 of them, etc.?
So I love this question. So there are two different environments here, and I'm 100% brutally honest with the community from the very beginning. There is the production area, and the VST standard is quite old. It aims to support everything, but it doesn't support the innovations. And it brings a lot of problems for people who are bringing something totally new to the industry. So we are managed to run like 150 of instances in the VST part of the GPU per 1 millisecond latency on my RTX 2080. But in the test area, without VST processor and that sort of things, I managed to run 700 of delays with the infinite impulse response filters within 1 millisecond buffer, within the 1 millisecond buffer latency, 700 on GTX 1070. So the technology, the core technology, the scheduler, we improve this constantly, and we improve this number of running simultaneously of all of the different plugins without the VST part continuously. So this 700 number is not the final one. I think that we can hit for the 1070 up to 2000 of delays. So this is something we done in the test area, but in order to bring it to the VST, we have to get the, I don't know, we have to figure out how to control the CPU threads of the DAW, because they simply sleeping and doing nothing, and that's a big problem for us. But I think that we know how to manage them, because we recently had some call with Steinberg, and I think that they will help us to deliver the final level of performance to the production area, because, well, why not? And this level of bench performance, this could be extended over the new devices coming, which is great, because you don't need to do anything else. You write code once and it will work for the RTX 2080 from the GTX 1070 to RTX 2080, RTX 3090, whatsoever. Many CUDA cores, many RTX Tensor cores, more power, more performance, faster results, lower latencies, or lowest latency at all, just bring more instances. So yeah.
Right. Thank you. So I guess one kind of very direct question from Jacob K. Guitar is, how mature is this technology?
This is mature enough to run the beta program, I hope, this summer. We actually announced to run this in April, but we are not managed to register the intellectual property first. And we are not going to deliver any binaries outside of the company unless we will register that, because, well, we spent 5 years on it. Sorry.
Yeah, of course. Yes, that's very sensible.
We will do that. We will open it, and I think that the time period to deliver from beta to the production to the commercial version will be like half a year. So I think that in the early 2022, hopefully we can deliver the commercial version that will work on different hardware setups of many users, and we can run different types of plugins. Also, we are making the multi-layer synthesizer. So
okay. Yeah, thanks. Well, I'm sure we can all can't wait to see this actually out in the wild. Like, this is really exciting technology. So I guess to wrap up, I have one last question, which is, where can we learn more about this? Do we have a website? Do you have a blog? Is this documented anywhere where people can read up on how it all works and everything you talked about today? Like, where should people go? Where's like more info?
Yeah, so currently we published the gpu.audio website. Please follow this website, sign up for the beta if you want to receive the beta and help us to deliver things faster. If you're the developer that is really interested in opportunity to bring the GPU audio powered product with the time, and first of all with collaboration, because the technology is very complex, and we want you to help you for free to deliver your version of the product, new product, or product that exists already. Please also sign up for the SDK request following the gpu.audio, and soon we will open the corporate web blog and we will post everything there, and you guys can follow this blog. I will also announce it. Actually, if you guys like the Audio Programmer YouTube channel, if you allow us, we wanted to, to start delivering the beta with you, if you allow, like within a couple of months. It can be another episode of the Audio Programmer, so we can both discuss how it works, how it can be run on different DAWs with different types. So yeah.
Okay.
Yeah, that would be amazing.
Great.
So just to everyone, the address is actually gpu.audio. Is that correct?
Yeah, we own this domain.
Okay, great.
Yeah, this is that address. Yes.
Awesome. Well, that's very promising. I'm sure we were looking forward all to actually learn about the beta phase and see if you actually have a bit more to show in a few months. And I think it's going to be super exciting.
Yeah. We wanted to share with the community that soon we will release the video, and we will share it across our social media accounts. We actually do not support them well. I'm sorry for that, but soon we will release the video where the GPU needs the CPU in terms of application of reverbs, because, well, this is well parallelized algorithm, and we want to show you all of the benefits of the GPU audio technology. Stay tuned. Thanks a lot.
Thank you so much for being with us tonight. And yeah, this is super exciting stuff.
Oh, I'm on mute. Yes, thank you very much to the GPU audio team for that fantastic presentation. And yeah, it seems like some real groundbreaking stuff. And I'm looking forward to us having some future collaborations where we'll be able to share more.
Yeah, looking forward to it. I believe that the audio programmer community is a top-notch community. You guys actually do the great job. You're uniting people that are willing to bring more audio plugins, commercial, for free, whatsoever, to learn more about the programming part. And we're definitely looking forward to partner with you in the future.
Amazing. I can't wait. Great. So thank you once again to the GPU audio team. And also another quick thank you to our sponsors, Juice, Sonics, and Focusrite for helping to support the Audio Programmer Meetup.